Hello, Science 14s. I'm here to work with you again. Today we're going to deal with section A2.3 and 2.4, talking about acids and bases. This begins on your student notes package on page 19. And without further ado, we're just going to pop right into it and see if we can't figure out what it is about acids and bases that you need to know and remember from days of past, okay? So, uh, acids and bases are opposites of each other, okay? They're on two sides, literally, of a spectrum, of a scale. Starting with acids. Acids are corrosive. That is, they eat through stuff, whether it's flesh or even metal. Acids can eat through metal and make them weaker and dissolve them away. So that act or that ability to eat through it and sort of dissolve, for example, metals is called corrosiveness. So acids are corrosive. If you were to taste some, and I don't suggest you use this as an indication of whether something, to test whether something's an acid or base, but if you taste some common acids that you're probably sure of, like lemon juice, then you'll notice very quickly that they are sour tasting. So on the flip side, let's just skip over here to two for a second. How would you categorize or talk about or explain or describe bases? Well, if you had some, if it was a weak enough base, or if you were silly enough to do it to a strong base, and you sort of wiped it between your fingers, you'd find very, very quickly that bases are slippery. All right, they're slippery. They're also corrosive. And the other word we often talk about is, again, if you were to taste them, and we don't suggest that you ever use taste as a test, but there are certainly some basic things that you have tasted. Well, they're bitter. Okay, so acid and base are like two opposites, just like sour and bitter are like opposite sides of the taste spectrum. All right. Now, there are some very common acids and some very common bases that you probably run into every day or know about or at least hear about. This one here, hydrochloric acid, hydrochloric. Okay, that's stomach acid. That's the stuff that helps dissolve foods in your intestinal system, in your stomach, and it doesn't eat through your stomach lining, the cells, like acids to do, because your stomach is lined with that mucousy, that really slimy mucus, and that actually helps deter the effects of acid on your stomach lining. Nonetheless, hydrochloric acid, very common acid you've heard about. Here's one that you've probably tasted: vinegar. Vinegar is acetic acid. And it's commonly used in cooking and baking and all sorts of things on your salads. And you get a sense of, when you've tasted vinegar, how sour it is. Another common one, you can pick any of the citrus fruits, but lemon juice. And it's got an acid called citric acid in it. And finally, let's give another chemically sounding acid that you're probably familiar with. Let's call it sulfuric acid, H2SO4, sulfuric acid. And that's a very common acid in batteries, in car batteries, or any wet cells, go-karts and golf carts and various things. All right, so there's some examples of common acids that you've heard about. You deal with bases as well, but something tells me they're just a little bit less common. So what are some common bases that you at least have heard about and probably do have in your home somewhere? So the first one is ammonia. Ammonia. And you've probably smelled that if you've ever smelled Windex, for example. There you go. That's an example of a household base. Another kind of base or basic solution that's pretty common is bleach or chlorine bleach, which is NaClO. ClO. It's a chlorate. Okay, so and if you smell anything, even in the pool, you know that chlorine smell that comes from a solution made with chlorine and water, which well, a chlorine compound and water, which together give you that basic that feeling. So ammonia and and chlorine bleach are very obvious, very they're not the most common substances, but I'm willing to guess and to bet that most of you have these in your house. And they're very unique from their odor. Not all bases smell, but these two really do. So if we were looking at some other examples of bases that weren't very odorific, didn't smell very much, well, here's one, baking soda. Okay, and this is, or otherwise known as bicarbonate soda. That's NaHCO3, bicarbonate of soda. Very common, use it as a leavening agent in flatbreads or in baking and stuff like that. This is one that you probably don't have in your home, but and again, it's related to the ammonia. This is ammonium hydroxide. Ammonium, just very common. This is NaOH. Very common in chemical processes. In fact, I do believe I've got some in my list of chemicals here. Yep, there we go. Look at that. Ammonium hydroxide. I happen to have that. I have some, there's some lemon juice, yeah. And there's some hydrochloric acid. So you can see, you know, they're clear, often colorless liquids. Okay, so you can't tell them on color. You have to be able to tell them on their properties, tell them apart. So acids and bases, again, are two sides of a spectrum, right? And you don't know this yet, but you're going to, well, we're going to explore it down here on these notes. Acids can be measured on a scale, so can bases. But generally speaking, acids have a very low value of pH, something between 1 and 6. Bases, on the other hand, have a fairly high pH, between 8 and 14. So the pH scale, as we'll discover in a moment here, goes from 0 to 14. So the low end are acids, the high end are the bases. So acids and bases are opposites, as we've pointed out. What do you suppose happens when you mix them together? Well, you get a chemical reaction, and what's happening chemically is that they're sort of canceling out each other. They cancel each other out. And the scientific word for that is neutralize. All right. So we're interested quite often in trying to figure out how to differentiate and how to tell acids and bases apart. You don't want to get into the habit of tasting them, because if it's a strong enough acid or a strong enough base, you can do your mouth parts a lot of harm. You can burn yourself. They react with water, and in low concentrations it wouldn't hurt you, but in higher concentrations, and how do you know whether something is a high or low concentration, it can really do harm to your body. So we try not to use taste, even though acids tend to taste sour and bases tend to taste bitter. We try not to, because of the sad effects you'll have if you ever were to taste something strong. So we use a number of chemical tests, and one of the most common is the litmus test. And you may have heard that as an expression in literature or in science or in the news. The litmus test of the presidency and so on, right? The test which tells you one thing or another. Well, there's two kinds of litmus paper that we use. We use blue litmus paper and red litmus paper, and they both respond differently to acids and to bases. So blue litmus paper starts off as blue, of course. Well, that's where you get the name from. Blue litmus paper starts off as blue, and it turns red in the presence of acid. So it goes from blue to red. Red indicates acid on blue litmus paper. Well, if blue litmus paper starts off as blue, what do you think happens when you expose it to a base? All right, we know the well, we think, at least I'm telling you here, that blue litmus paper turns red. What do you suppose happens with blue litmus paper in the presence of a base? Interesting thought. I'll show you in a moment what happens. Red litmus paper starts off red, and red litmus paper in the presence of a base turns blue. So very quickly here, no matter whether you're talking red litmus paper or blue, it looks like you are getting this indication. Blue is base. You thought it was aces base. Nope. Blue means base. All right. So if you get any kind of litmus paper and it looks blue, then it is probably indicating that it's a basic substance or base in solution. All right, we're just touching the surface here, right? We're not going into any great amount of detail, and we're going to come back to the pH scale. We're going to come back to what litmus paper looks like and the different kinds of tests you can do with it. Okay, there's some blue litmus paper there. Okay, but just to finish off the line of discussion here, the line of thinking, the units or the words that you use or the scale they use for acids and bases. Well, the units of acidity and if you're going to put a word to talk about how acidic something is, how the words we use for something that's acid is acidic, and the words we use for alkalinity or basic basic is alkalinity. So here's the word especially here. Alkalinity or alkaline and basicity or basicness are sort of two ways of describing the bases side of the substance that we're going to be looking at. Acidic or acidity is the other. And we use a scale called the pH scale, oddly enough. A power of hydrogen. If you're interested in the origins of the idea, you might not understand what that means, but it has to do with how many protons are in the solution. The more protons you have, the more acidic something is. And it's all quite interesting. You'll discover this and you'll delve into more detail, even in Science 10, but certainly in Chem 20. The pH scale is a scale of 0 to 14. It goes from 0 to 14. Where 0 to 6 is the acidic side, and we were talking about low pH is acid. That's what we're talking about. So it's an actual number on the pH scale of 0 to 6 means that it's acidic. A number between 8 and 14 means that it's basic, and then that perfect 7 means that it's perfectly neutral, perfectly balanced between the two. If I were to take a look and just very easily and very quickly take a look at blue litmus paper and red litmus paper and how they would respond in the presence of both an acid and a base. Well, here's some hydrochloric acid, and at this point I will throw on my safety glasses, because whenever you're working with a chemical, whether it's mild or strong, dangerous or even innocuous, you always have to pretend and treat it as though it were. I'm going to put a little drop of acid on the red pH paper and a little bit of acid on the blue, and you can see very clearly that acid makes blue go red. Red is the color associated with acids. And let's take a little bit of sodium hydroxide, which I'm telling you is a base, and we'll add it to blue litmus paper. The key color for base is blue. So acids are red, bases are blue. I love chemistry, and I hope you do too. And take a look at turns red litmus paper to blue. There you go. Just a very quick overview of the basics of acids and bases. The basics of acids and bases. See what I did there? I made it funny. Acids and bases. The basics. All right, here we go. Let's see if we can't finish off this topic on acids and bases by looking at section 2.4, which is page 20 of your student notes package, which sort of looks like that. And see if I can't set up a couple of very simple demonstrations of a reaction that you're going to see as well. All right, acids and bases in action. Well, would it surprise you terribly if I told you that you use that relationship between acids and bases in everyday life, every single day? Well, I'm not saying you bake bread every single day, but if you were to, and if you do some cooking, you do acids and bases. You use the idea of acids and bases and the complementarity of acids and bases all the time. So if you're baking, for example, yeast requires a set range of pH values for it to be able to do its stuff, to be able to convert sugars into carbon dioxide and to make your breads or your cakes fluff out. So you have to be thinking about that pH. Well, you don't think about the pH balance between all the ingredients of your recipe. Your recipe does it for you, right? Tells you how much salt and sugar and water and so forth to add, and all of that helps affect how your bread will leaven and how the yeast grows. We do think about it in a lot of issues, a lot of situations where we're baking. In terms of just general cooking, cooks, and you may have heard this if you've taken a culinary class, cooks are really, really interested in the balance of flavors. And often we're balancing things like acidity and spiciness or sweetness. And it's not something they go in there with pH paper to decide on and to test for, but it's certainly something they think about when they're doing stuff. In terms of health, pH comes into play, and you will be tested for this in terms of blood chemistry. Whether you've got enough potassium salts and electrolytes in your blood that would allow your cells to be able to do their job and allow for the efficient and equal exchange of oxygen, for example. So blood chemistry, they'll also test urine for pH imbalances, right? Because it can indicate if there's a problem in your urinary tract. So we use pH strips and test strips all the time in the medical field. And finally, in sanitation, well, again, it's not something you think about every day, but in sewage treatment, for example, we want to keep a balance in pH because at certain pHs, certain kinds of bacteria, which help in the decomposition of human waste, for example, can be, at certain levels of pH, those bacteria can be harmed. And you need to be able to have those bacteria thrive so that they can do their stuff. So sewage treatment, for example, is something where we might be thinking about pH levels as well. And they'll go in there with test strips and test kits to make sure that that things are at the right balance. So one important aspect is that strong acids and strong bases are corrosive. They can eat through tissue, and they can even eat, in case of metals, or in case of acid, eat through metals. Okay, so strong acids are generally 0 to 4. Strong bases are usually in the 10 to 14 range, and you can have mild acids, pH 5, pH 6, or mild or weak bases, pH 8 or pH 9. But when you get into that 0 to 4 range, when you get down low on that scale, those are considered to be strong acids. and the 10 to 14 range, like Lyes, for example, that's used to make soap, or Drano. Um, when you get into that range of bases, then you can uh, also cause damage. So you have to be very careful when you handle them, for example, because they can eat through flesh and tissue. So some common ideas and some common things that we use as, I'm going to give you two examples here. Um, Drano. Drano is a base, and if you were to have it come into contact with your skin in the presence of moisture, it would start dissolving skin. In fact, that's what Drano is designed to do. It's designed to eat through fats and organic matter that's stuck in the drains. And it does that literally by dissolving it. And if you were to place it on your unprotected skin, well, it would start being dissolved as well. Dissolves organic matter. You want to be very careful when you store these materials because they have the ability to dissolve or eat through different stuff. Storage is a very big consideration. For example, very, very strong acids and bases will often be stored in glass containers because, with the exception of one notable acid, that's hydrofluoric acid, glass seems to be fairly inert when it comes into contact with most of these substances. And finally, you want to be able to keep out of reach of students, animals, pets, that kind of thing that might get into them because of the damage um, that it can cause if it's been misused or it's been applied somewhere where it shouldn't. All right. So the two examples then of strong acid, strong base we're going to use. The first one I know I've mentioned over here is Drano, and it's used in sewage lines to dissolve that organic matter that might have been clumping up. So things like hair and fat and grease and congealed gunk in your drains. Well, the Drano does a fairly good job of just eating right through it and dissolving it and allowing the water to flow through the trap and do its thing. An example of a strong acid you might have. Now, not many of us have strong acids, but if you happen to have a pool, say, you would have a product more than likely called muriatic acid. And muriatic acid is just a consumer name, just like Drano is a consumer name of a bleach and of a very strong base. Muriatic is just a consumer name or a consumer word for hydrochloric acid. And you would use that in pools to help maintain the pH levels, but also to help wash and scrub away um, deposits of film and soap and scum along the water line. So I've brought to the forefront examples of these two acids and bases because I'm going to tell you one important thing that you should also be aware of and be careful about, and that is that they should never really, under uncontrolled circumstances, be mixed together. See, when acids and bases of any sort are mixed together, they can neutralize each other. And I'm going to show you a very short, a very small, very simple neutralization reaction right now. I'm going to put my goggles on. I'm going to take a very common acid that you have in your house called vinegar, and I'm going to throw it in here. And just a couple drops here. And I'm going to throw a couple drops of another very common base that you could have, that I know you have, and it is sodium bicarbonate. Whoops, there we go, sodium bicarbonate. Sodium bicarbonate is just another word for baking soda. Take a look what happens here when I mix sodium bicarbonate, and acid. There you go. Now, that's not a huge vigorous reaction. You see the bubbles forming, okay? Cool. So that's an example of a neutralization reaction. Now the problem is when you mix certain acids and bases together, you get products that are formed that are pretty nasty. So one of the things you want to be very, very careful of is when you mix, for example, and this is something you definitely, absolutely do not do, mixing bleach with ammonia, say window cleaner, like a Windex or something. Chlorine bleach and ammonia in Windex. When you do that, you get a very toxic substance and gas produced, and you can do yourself and whoever's in the area with you a lot of harm. Because it gives off a gas, gives off chlorine gas, and you can actually do a lot of damage with that. So, I mean, if we look at examples here of what we saw when we added some vinegar, a very mild acid, with sodium bicarbonate, a very mild base, bubbles. You can also get evidence of new substances being formed. New substance being formed. Because when you're mixing an acid and a base together, you're actually creating a chemical reaction and creating a new substance out of it. So finally, not to scare you, but neutralization reactions aren't always bad. Everyday acid-base reaction is the one we just showed there, which was baking soda and vinegar. Okay, there's baking soda and acid. Here's an example of where you use that every day to as a benefit and as a beneficial thing when you brush your teeth, because toothpaste will have that bicarbonate of soda, and it will react with the bacteria poop that's left on your teeth. Bacteria poop are acids. That's the acid that eats through your teeth and causes cavity. So the bicarbonate of soda, baking soda inside your toothpaste actually neutralizes the acids on the surface of your teeth. That's why you get a little bit of tingly sensation sometimes, or a little bit of foaminess, and it neutralizes the acid, and presto, bingo, no more cavities if you do it regularly enough and properly. Let's see, no more cavities. There we go. So there we go. Acids and bases in action. We use them every day and in everyday life, whether you realize it or not. All right, go forth and conquer. Answer your questions in your student workbook, and happy aciding and basing. It's all very basic. It's all very basic. See what he did there? All right, cheers. Good day, good day. Ready to do some science. I'm going to play around with some acids and bases with the idea of trying to figure out how to tell whether a substance is acidic or basic. And to do that, we're going to use a couple of apparatus here. You'll notice, first of all, that I am wearing eye protection. I'm not dealing with anything too terribly dangerous today, but the point is that you treat every chemical that you play with and observe with and experiment with as though it were dangerous, because A, you never know what you have and whether it can be harmful to you. And B, if you get yourself into a bad habit and start being lax and lazy with some chemicals, then that could turn around and bite you in the butt later on. So you don't want to be forgetful. You want to treat everything like it is the most dangerous substance around, and always take care. So here's the first piece of apparatus I'm going to deal with here. This is a spot plate, and I've got 3 substances in different dispenser tubes here. The first one I have is sodium hydroxide, and if you take a look at the molarity or the concentration, 0.1 molar solution. That is not a very strong a very strong base at all. You can put it on my skin and it likely wouldn't cause any problems. Now, if you put it into a cut or if you put it into some of your mucous membranes like your mouth or your eyes, then you could definitely be feeling some discomfort. But I'm not going to seriously harm myself if I have a mishap. But still, we're going to treat it like the chemical it is. On the right, we have some, again, very dilute, 0.1 molar hydrochloric acid. This is the acid that happens to be in your gut, in your stomach, that helps digest food. And that kind of stuff that you taste if you burp up something or if you are throwing up and you feel that burning sensation, that's the hydrochloric acid from your stomach. And finally, because we need a control when we're dealing with tests and figuring things out, we're going to use distilled water. And you'll be able to see how each one of these substances reacts to the different tests, the different paper we have. We're going to be using a blue litmus paper on the one hand. We will be using something called red litmus paper as well. And then finally, we're going to use some broad spectrum pH paper, which is a really good indicator for, it's not terribly accurate sometimes, but it's a good ballpark that you can use to help determine whether something is an acid or base and also how strong an acid or base it is. To handle all of these, I'll be using, not rubber gloves today, but I will be using forceps to dip in. And we'll be comparing the colors and trying to observe what happens. So let's start with the setup here. I'm going to put a couple of drops of my sodium hydroxide in 2 spots in my spot plate, and it's going to be on the left side. And I'm going to put some drops of the hydrochloric acid as well on 2 different spots of the spot plate on the far right. All right. And then finally, I'm going to put a few drops of my control substance, which is distilled water, and I'm going to toss that down in the spot plates in the middle. Just like that. All right. So once again, I've got 3 different indicated papers here, and I'm going to take a little bit of each, and I'm going to see how it reacts and responds to each of those. So here's a bit of blue litmus paper. Blue litmus paper is blue. And in the presence of a base, this is what happens to it. And you can see very clearly that blue turns blue in the presence of a base. Remember that this substance on the far left is that, the NaOH. All right. So let's take a little bit more litmus paper here and let us test how it would look in an acid. So here's blue litmus paper in acid. And you can see very clearly and very quickly the reaction that's happening there. It seems to turn blue litmus paper to an orangey red. All right. And then finally, let's take us a little bit of litmus paper and let's see how it would respond to the distilled water. There's the distilled water, and there I place it. It looks like distilled water, and anything more basic than it has no effect, makes no change to the litmus paper. All right, we're going to try and take a look at some red litmus paper now. So we're going to see how red litmus paper responds and reacts to an acid, to a base, and then to a neutral pH solution of pure distilled water. So once again, red litmus paper, and the name's a giveaway, looks sort of, well, very paley pinky yellow or orangey red. Okay, so let's place the red litmus paper in acid. And we're going to go down this one here now, okay? And let's see what happens. All right. So there is what you get. It turns, or it leaves, red litmus paper red. Let's take a look now when we do red litmus paper into a base. What color do you imagine now based on 3 examples of questions we've done, of tests we've done? What do you think red litmus paper will turn in the presence of a base? Was that what you thought? Well, there you go. Base goes blue, it looks like. Base goes blue. And finally, we'll put a little bit of the orange or red litmus paper into neutral distilled water, and there you see what happens there. All right, so it looks as though blue is the important color for base, blue base, BB, blue base, and that red is the predominant color for acid, red racid, red racid. Okay, it doesn't always work, but I think the blue and the base give you a good indication. All right, I am now going to take a little bit of my multi-spectrum pH paper. Notice what color it appears right there. On the camera, it looks sort of washed out yellow. In real life, the color balance is off a little bit, and that's really more of an orangey color. I don't know if you can tell where it belongs here, but it looks to be, well, it's kind of hard to tell, eh? Doesn't really fit anywhere in there. All right, so let's start by putting a little bit of pH paper on the water just to see. All right, so there it is. And if we were placing it around here somewhere, well, it's probably a little bit different. It really does look close. See, it doesn't match exactly the color you're looking for, but I think it's a little bit darker than pH 7, but certainly a little bit lighter than this iso. So it's very, very close to 7 here. You can see where, and you can see it's just turning a little bit. So I'm going to place it right around here, just so we can keep track of it. All right, pH paper into our base, sodium hydroxide. Well, if you take a look just at the scale here, we expect some colors in around that side here, right, for a base. And let's just see what happens. Look at that. Look, very dark, very close to, looks like pH 12 or so. Yep. I'll place that there. And maybe I'll place this over here just to show. And then finally, we'll take a little bit of broad spectrum pH paper and we'll see how it responds to an acid. Okay, and you can probably see what you expect to happen. We're expecting this kind of color down here. Let's see what we get. Oh, look at that. Low pH right around here. Okay. So just to summarize, let's take a look at this one. This is the base. It's not in this side. It's really down in this area here. So pH maybe 13. Do you see how similar those two colors are? Okay. So base pH 13. Neutral distilled water seems to be around the 7. It's really looking close to that now. So 7, good. And then finally acidic pH 1. See, look at that. Look at the similarities of the color there. So it gives you a really good indication. Blue litmus paper turns blue in the presence of a base, or stays blue, but turns red in the presence of an acid. Red litmus paper stays red in presence of an acid, but turns blue in the presence of a base. And finally, the broad spectrum pH paper seems to respond pretty well to both very basic, high pH value, and to a very acidic, a very low pH value. And that's all there is to it. Rock on, keep experimenting, stand back, do some science.